Welcome to The Explainer. Today, we're going to pull back the curtain on the hidden physics behind some pretty amazing everyday things. Like how your foot can lift an entire car, or how a massive chunk of metal like an airplane can actually fly. All right, let's just jump right in. So, how on earth can your foot lift a 1,350-kilogram car? Seriously, think about that. It feels like some kind of magic trick, right? But it's not magic. It's just some really, really cool physics that governs the world all around us. So to get to the bottom of this, we first have to talk about how stuff, and I mean both solids and fluids, reacts when you put it under pressure. When it gets pushed, pulled, and squeezed. So when you apply a force to something solid, say you're stretching a wire, the atoms inside it don't just give up. They create this internal force to fight back against that change. It's like the material's own internal pushback. And in physics, we have a name for that: stress. And, the result of that stress? Well, it's how much the object actually deforms. That change and its shape or size compared to what it was before, that's what we call strain. It's basically just a number that tells us how much the thing has changed. Okay, and this is where it gets really interesting, because it kind of flips our everyday ideas on their head. So let me ask you, which is more elastic, steel or rubber? Think about it for a second. The answer, well, it's probably not what you think. So yeah, most people would say rubber, right? But here's the twist. In physics, elasticity isn't really about how stretchy something is. It's about how well a material resists being deformed, and crucially, how perfectly it returns to its original shape. And when you look at it that way, steel is the clear winner. For the same amount of force, it barely deforms at all, and it snaps back perfectly. That actually makes it way more elastic than rubber. So how does all this help us lift a car? Well, for that, we need to shift gears from solids and start looking at fluids. The principles are kind of similar, but there's a powerful twist here that's going to unlock the whole secret to that car lifting puzzle. And this brings us to a brilliant discovery by Blaise Pascal. His rule, Pascal's law, is pretty simple. If you have a fluid in a closed container, think of the brake fluid in your car, and you apply pressure at one spot, that pressure is instantly felt everywhere inside that fluid, completely undiminished. And this is how the magic trick works. It's genius. You apply a small force to a small piston, which creates a certain amount of pressure in the fluid. Now, because of Pascal's law, that exact same pressure pushes on a much larger piston on the other side. And since force is just pressure times area, that same pressure acting on a bigger area creates a huge output force. And that right there is how your foot on a tiny pedal can lift a 1,350-kilogram car. Okay, so we've covered matter that's just sitting there under pressure, but what happens when we get it moving? Let's talk about fluids in motion, because this is where things get really dynamic. You know how when you put your thumb over the end of a garden hose, the water shoots out way faster? Well, there's a rule for that. It's called the equation of continuity. It basically says that for a fluid you can't compress, what goes in must come out. So if you make the pipe narrower, the fluid has no choice but to speed up to get the same amount through. And this leads to something that feels totally backwards, but it's true. It's called Bernoulli's principle, and it says this: where a fluid is moving faster, it actually has lower pressure. I know, it sounds weird, right? But this one simple relationship is the secret behind some of the most incredible things humans have ever built. Take an airplane wing, for instance. It's a perfect example. That curved shape on the top is designed specifically to make the air have to travel a longer path, so it has to move faster than the air going along the flat bottom. And because of Bernoulli's principle, what does faster air mean? Lower pressure. So you get the zone of low pressure right on top of the wing. So now you've got high pressure from the slow-moving air underneath the wing and low pressure from the fast-moving air on top. And that difference creates a massive net force pushing upwards. We call that dynamic lift. And that force is literally what lifts a jumbo jet off the ground and keeps it in the sky. All right, for our final piece of the puzzle, let's throw one more thing into the mix: heat. Because when you add energy in the form of heat, it can dramatically change how matter behaves. You've seen this a million times, right? Most things, when you heat them up, they expand, and when they cool down, they shrink. It's called thermal expansion. It's exactly how an old-school blacksmith would fit a metal rim onto a wooden wheel. They'd heat the metal so it expands, slip it on, and then as it cools, it shrinks and creates this incredibly tight fit. But then there's water. Water is, well, it's a total rubble.
It does not follow the rules. It behaves in this really weird way right near its freezing point. And this strange behavior is absolutely essential for almost all life on this planet.
So, as you cool water down from, say, room temperature, it does what you'd expect. It gets denser and it sinks. Pretty normal. But that only happens until it gets down to 4 degrees Celsius. That's the point where water is at its absolute densest. Because as you cool it down past 4 degrees on its way to freezing, the weirdest thing happens. It starts to become less dense again. The colder water actually starts to rise back up to the top. And what does that mean? It means that lakes and ponds freeze from the top down. The ice forms a layer on the surface, which acts like an insulating blanket, protecting all the water underneath from the cold air. And that's why fish and everything else living in the water can survive the winter. Okay, so heat also makes things change state, right? Like melting or boiling. But there's another weird thing that happens when you boil water. You've got a pot on the stove, it hits 100 degrees Celsius, and it starts boiling. If you keep cranking up the heat, the temperature doesn't go up. It stays stuck at 100. So where is all that extra energy going? It's being used to break the bonds between the water molecules to turn the liquid into steam. That hidden energy is called latent heat. And we're not talking about a little bit of energy. It takes a huge amount, over 2.2 million joules, just to turn 1 kilogram of boiling water into steam. That is an incredible amount of energy just packed away inside that vapor. So think about what that means. When that steam hits a cooler surface, like your skin, it instantly condenses back into water. And in that instant, it releases all of that massive stored up latent heat. And that is exactly why a burn from steam is often so much worse than a burn from boiling water at the same temperature. So when you put it all together, what's the big picture here? From lifting a car with your foot, to flying a plane, to the way a lake freezes over, these aren't just a bunch of random, separate tricks. They're all part of this single, invisible blueprint that governs how our world works. Understanding these rules is the foundation of all engineering, of everything we build. So the next time you see a bridge, or a pot of boiling water, or a plane soaring overhead, you'll know the hidden physics that makes it all possible. It makes you wonder, right? What other invisible rules are out there, just hiding in plain sight?